Okay, welcome to the Civil Engineering Materials FE review session. My name is Mike Angone. I'll be going through the review here today, and if you have a chance, hopefully you've been able to download the slides that go along with this particular presentation so that you can follow along and not having to write so much down, but just can kind of focus on some of the things I'm talking about throughout the video. Alright, so the FE exam, these are the topics that you can expect regarding civil engineering materials. Somewhere between 4 to 6, as you can see here, somewhere between 4 and 6 questions are covered on the FE exam regarding civil engineering materials from the different topics that I have listed here. Many of these topics here you've covered in some type of civil engineering materials course, and such as concrete mix design. Asphalt mix design might be covered in some courses. Other courses, it's not covered in the CE materials. It's more covered in the in a pavement design class or a traffic design class. Some testing methods, again, following ASTM specifications for steel, concrete, asphalt, aggregate. Some of the properties of aggregate, of course, as well as properties of metal, wood, and masonry, things that are, again, common materials used for civil engineering construction. In this particular video, I'll just kind of go out and say that I'm not going to really cover much in the form of asphalt design. It's not covered much in the design component's not covered much in the civil engineering materials codes and specifications course. So it's covered in transportation engineering systems. So I'm going to refer to that particular class for the asphalt mix design portion. However, I will go over a little bit about performance grade in the super pave program, which is a big part of asphalt construction, and probably more likely what you would see related to a asphalt kind of question on this exam as opposed to an actual mix design question. Alright, so I'll go step first with the concrete mix design. So again, keep in mind, what are we doing when we're talking about a concrete mix design? So we're determining what are the batch ingredients or proportions of cement, water, and aggregate that we need in the particular concrete. And in some cases, we know we're going to add admixtures. So admixtures, again, are things that are different or things that we add to concrete that are not cement, water, or aggregate that change or modify some of the properties of that concrete. So common admixtures are something like superplasticizers, right? So water reducing agents, things that make concrete maybe more workable, easier to consolidate, but don't require us to add more water and lose some of that strength. And there are other things as well: fly ash, slag, air entrainment. Admixtures, chemical admixtures to provide little air pockets to help with durability, things like that. All right, these are all examples of admixtures that we can put into concrete. So that's what we're doing when we talk about a mix design. And again, mix designs are based primarily on three things: workability and consistency, strength and durability, and of course any material that you deal with in, no matter what it is, civil engineering or mechanical engineering, whatever it might be. And whether we're dealing with wood, timber, masonry, metal, concrete, doesn't really matter. Strength and durability are key. All right? So the material always must be able to have appropriate strength to handle what it needs to, carry the loads that are going to be required of it. And it also has to be durable. We can't have that material breaking down due to environmental effects or other type of effects. It can't disintegrate or anything so easily. All right? So we want to make sure it can withstand environmental elements and things like that. And of course, economics goes along with anything that we do in engineering, making sure that when we deal with costs, that the cost is reasonable. Right. So strength and durability, again, mix is usually designed based on compressive strength. All right, especially when it comes to concrete. All right, concrete is a material that's very good in compression, as we know, and that's why what it's used oftentimes for things like columns and walls, things that are oftentimes primarily in compression. We will see concrete often used. When it comes to durability, so again, water tightness, something that's important, keeping the chemicals and keeping some of the environmental effects, so to say, out of the concrete from permeating into the concrete and causing some disintegration or some deterioration to occur. And of course, freeze thaw is also a big part of when we come into durability, and having entrained air entrainment admixture is something that helps a lot when it comes to improving the durability of concrete, especially in areas, like I said, that do have a lot of freeze-thaw effects. Now, we do know that there are some trade-offs when we have air entrainment, right? Because we're actually introducing, with these chemical admixtures, we induce a little air pockets, air voids, we create void spaces, and we know when we create those void spaces, that can minimize or reduce a little bit of the strength of the concrete. So there is a a balance or a trade-off, so to say, between having using air for durability as well as using air to kind of, and when we use air, we kind of can minimize the strength a little bit. So there is that trade-off that we will see. But again, air entrainment, again, is an admixture. It's a chemical admixture that's put in the concrete to create these little air bubbles, little air voids. And again, remember what is happening there. It creates a space for water to expand when it freezes. All right, so that really does help keep the concrete more sound, so to say, and reduces some of the cracking, and it reduces some of the spalling effects that might occur from that water freezing and pushing against aggregate and other things like that in the concrete and causing parts of it to break. All right, so when we're selecting our ingredients, what are we basing this on? So we're basing it, number one, on workability of the mix. All right, so how workable, how easy is it to work with? Having as little cement as possible. So we remember when we talk about cost in particular, cement costs a lot more than aggregate does. So the more cement we have, the more costly the concrete is going to be. Also, when we talked about creep effects, for example, we remember that the cement paste is actually the part that creeps more so than, well, that is the part that creeps, not the aggregate, right? So having a higher cement content will create a little bit more creep in the concrete, but also as little water as possible, all right? So the cement and water together form the cement paste that acts kind of as the glue, again, as we mentioned previously, all right? Well, again, when we think about shrinkage in the concrete, shrinkage is due to water leaving the concrete. So when the water leaves or evaporates from the particular concrete, then the concrete will start to shrink, and those shrinkage can create stresses in the concrete and create cracking. All right, so the more water that we have, the more shrinkage will occur, the more cracking that will occur, and we can create some problems in that particular case. All right, so that's one thing about when we think about water. We also want to think about the effect that water has on the strength of concrete, right? And we'll come down here just for a quick second when we talk about water-cement ratio. And we recall we drew this, or you should have seen this in the materials class when you're looking at water-cement ratio versus the compressive strength of the concrete. You remember that as the water-cement ratio increases, the compressive strength of the concrete decreases. So as we add more water to the mix, yes, we can help make it more workable, but we also run the risk of course, reducing the overall strength. And that's where things like water-reducing agents or superplasticizers come in handy, in that we can add these admixtures to the concrete without having to increase the water-cement ratio to make it more workable. Right? And another thing here is that coarse and fine aggregates should be proportioned to achieve a dense mix. All right, so again, the more dense that we can make a mix, the stronger the concrete will be, and also the better the properties of the concrete will have, more water tightness and things like that, which will help overall improve the performance of the concrete. Okay. So proportions are based on, we've kind of said, workability. Another thing is void content, water-cement ratio. Again, water-cement ratio being one of the big ones because it has a direct impact on the overall strength and durability, really, of the concrete. And as we do a mix design, we got to keep in mind or just remember that we're starting out with kind of a trial mix, so to say. This is kind of the first round or first batch that we come through and we put together. And this first mix is, so to say, based on, or does not include, I should say, or account for two main things. Number one, any surface moisture or any moisture that might be in the aggregate. So if the aggregate's being stored, say, outside, there might be some moisture contained within the aggregate that we need to account for. And the other thing is the absorption of the aggregate. Okay, so that's where we take this particular initial trial batch and we have to make sure we go through and we adjust that to account for the absorption and surface moisture. Now, why are those things important? Okay, why is it important that we go through and account for these? Well, if we think about surface moisture first, if you have surface moisture on the aggregate, that's going to add additional water to the concrete above what you've already designed for. So if you've designed for the concrete to have, say, 300 pounds of water per 27 cubic feet, okay, I'm just making up a number here, but suppose you have 300 pounds of water per 27 square foot or cubic feet of concrete. Well, in that particular case, you have a certain water-cement ratio, and that water-cement ratio is going to give you a anticipated strength. Now, if I have some surface moisture in the aggregate, Now, and I'm adding that aggregate into my mix. Now I have all that surface moisture that's adding additional water. That's adding additional water into the mix. And what is that doing? That increases the water-cement ratio and decreases the strength. So if I'm designing for a certain water-cement ratio and a certain strength, and I'm adding all this aggregate that has surface moisture, the strength that I'm actually going to achieve in the concrete is going to be less because I'm adding more water that I didn't initially account for. All right, so we have to make sure we account for that surface moisture. The other thing is the absorption of the aggregate. So the absorption of the aggregate can affect two things. Number one, it could take some of the water out of the cement paste, and that will create some shrinkage in the concrete. All right, so that has to be accounted for. But the other thing we have to keep in mind is water is very important for concrete to fully hydrate. And we recall that back here, we remember that we have to have a minimum water-cement ratio of 30% approximately to achieve full hydration. Okay, so again, hydration is that process where the concrete undergoes hardening. All right, which where it gains its strength. And if we have aggregate that's very absorbent in there, it's going to take a lot of that moisture out of the cement paste. It's not going to allow full hydration to occur. And if that happens, then we're not going to achieve the full strength that we need in the concrete. So it's very important that we actually measure or determine the absorption of the aggregate and if there's any surface moisture on the aggregate before we just go ahead and use it in our mix. All right, and there are certain laboratory standards that we need to follow, ASTM standards, that will actually allow us to determine those things. Okay. All right, so one of the big things is to calculate, as we mentioned, the water-cement ratio. And again, water-cement ratio is a very easy thing to calculate. And oftentimes, when I think about what type of questions could be asked on an FE exam, this is a very easy question and something that can be easily asked on the exam. All right, so when we're looking at the water-cement ratio, it is just equal to the weight of the water divided by the weight of cement. Okay? Or the weight of cement is just equal to the weight of the water divided by the water-cement ratio. But that's what this means, W over C. The weight of water to the weight of cement. And again, it's important to remember this is the weight and not the volume. Okay? So the weight of the water and the weight of cement, not the volume of water and the volume of cement. Okay? So on the FE exam, a very easy question could be, okay, here's a water-cement ratio of something. Here's the weight of water. Determine what is the weight of cement. Okay? And again, they're not going to tell you that WC is the weight of water to weight of cement. They're just going to assume you know that. So again, that's what this ratio means, and just keep that in mind. Very easy question to ask on that. All right, another big thing, as I mentioned, we have to, when we're looking at a mix design process, is to go through and determine how much fine aggregate we need in the mix. All right, so there's a step-by-step process that you follow to determine the amount of coarse aggregate and the amount of water and the amount of cement that we need to add to the mix. And at the end of the day, when we know how much water, how much coarse aggregate, how much cement, how much air we want to add to the concrete, the last thing to determine is how much fine aggregate. Well, the fine aggregate is typically the last part of the mix. Okay, so if we've already calculated or know the cement, how much coarse aggregate, how much water, how much air, and we know what the total concrete we need for the particular thing we're designing for, maybe it's a slab or a beam, whatever it might be, then the difference in these volumes is just going to give me how much fine aggregate's left, okay, or how much fine aggregate we need to make up the remaining volume. Now, the one reason why I bring this particular slide up is more so just to kind of recall this particular equation here, which is on specific gravity. So again, specific gravity is the specific weight or the unit weight of some material to the unit weight of water. Okay, and the unit weight is calculated as the weight of something divided by the total, or divided by the volume. Okay. Now again, when we're saying unit weight, we got to keep in mind this is weight and not mass. Okay, so there is a distinction between mass and weight, and obviously the difference between the two is gravity. All right, so whenever you're dealing with specific weight, gamma, you have to make sure you're using weight and not mass. You could also use density in this particular equation, say the density of some material divided by the density of water, in which case that would give you also be a valid form of the specific gravity, but again, density uses mass. Okay, So basically I'm showing this equation here because once we determine the volume, I can just easily plug it into this particular equation. If I know the specific gravity of the material, say the fine aggregate, I know the unit weight of water. That's usually just a constant value, depending on the system you're using, metric versus SI. And if you calculate the volume, you can easily get the weight and how much weight is going to be needed of that fine aggregate. Okay. Again, so this is just my main reason for bringing up this particular slide is, again, just to kind of recall how to use this particular specific gravity equation in your calculations. All right, calculate the ingredients required to make the desired amount of concrete. So again, if we take a look here, we have a total volume of concrete is going to be equal to the volume of cement plus the volume of fine aggregate plus the volume of coarse aggregate plus the volume of water plus the volume of air. Okay, so we really have all these different components that come into making concrete. And again, we can, if we know that we have 1 part cement, 2 parts fine aggregate, 3 parts coarse aggregate, and 0.4 parts water, we can use an equation such as the one we see down here to determine the total volume of concrete. Okay, so this is just another way of kind of presenting this type of mixed design or this type of problem. And if this is 1 part cement, this is 2 parts fine aggregate. Basically what this means is, this is, when we say 2 parts fine aggregate, we're meaning that the fine aggregate is twice the weight of cement. And when we say 3 parts coarse aggregate, we're saying that the coarse aggregate is 3 times the weight of cement. And we're saying here with 0.4 parts water that the weight of water is 0.4 times the weight of cement. Okay, so notice how everything is basically in relation to the weight of cement. We make weight of cement 1, and everything else is in relation to it. So that's why we can come down here and we use this particular equation, and we can fit in here that the weight of cement is just going to be 1 times the weight of cement. The weight of fine aggregate is 2 times the weight of cement. The weight of coarse aggregate is 3 times the weight of cement. The weight of water here is 4 times the weight of cement. And then we have how much air we decide we're going to add as well, based on different ASTM tables and charts. Or not ASTM, sorry, ACI typically is the tables or charts that we're going to use. Okay, and again, we have the specific weights, which are specific gravities, excuse me, that are typically known for the different types of aggregates that we're going to be using. All right, I kind of mentioned this already. We have to find or adjust the mix. So again, when you're going through the process of a mix design, the very last stage is to adjust for free moisture and for absorption of the aggregate. And we talked about the importance of this previously in one of the earlier slides. All right, so again, like I was mentioning previously, this is a very easy and simple example problem that could be asked on an FE exam, and that is, all right, I have 14.3 pounds of cement, and I'm used to make 3 6 by 12 inch cylinders of concrete. How many sacks of cement are required per cubic yard of concrete? Okay. All right, so this is, again, a very straightforward problem. The only thing is we have to kind of remember how many pounds are in a sack of cement. All right, that might be something you want to remember. There's 94 pounds in 1 sack of cement. All right, so here's the solution to our problem. So we have 14.3 pounds of cement used to make 3 6 by 12 inch cylinders of concrete. So in 3 cylinders of concrete, we have a total volume of 0.59 cubic feet. Okay, and we know that there's 14.3 pounds of cement within that 0.59 cubic feet of concrete. So if I take the 14.3 pounds of cement, divide it by the volume of concrete of 0.59, we get, and we convert from cubic feet to cubic yards, we're going to see we have 654 pounds of cement per cubic yard of concrete. Okay. Well, we know here that there is 1 sack of cement is 94 pounds. So we have this weight here, which we found, divided by 94 pounds per sack, and I have 7 sacks of cement are needed for this particular mix. All right, so a very straightforward, simple problem, but again, just keeping in mind this relationship here of 1 sack is equal to 94 pounds. Also keeping in mind here this relationship of weight divided by volume to give me this particular result here. All right, so here's another very simple, basic problem, and in my opinion, probably more likely to see some problem like this than maybe the previous one, although maybe be ready for the previous problem. But this is a really a good problem here, and I've heard from students in the past this type of problem being asked, so I wouldn't be surprised if it is asked. And it is very basic and very simple. It's if a weight of water required for a trial batch of concrete is 270 pounds per cubic yard, and the WC is 0.55, what is the amount of cement needed? So in this particular problem, they're relying on you understanding what is WC. They don't tell you the water-cement ratio. They say WC is 0.55. So you have to know what WC is. Again, as I mentioned previously, WC is the weight of water to the weight of cement. So if I'm looking for the weight of cement, I'll just solve for it out of this particular equation. And I have 270 pounds of water. I divide it by the water-cement ratio, and it tells me that the amount of cement that is equal to is 491 pounds. Okay, so again, a very simple, basic problem, nothing too difficult, but again, just relying on you understanding or remembering or knowing, I should say, what is WC. It is the weight of the water to the weight of the cement. Okay. All right, so that ends my primary discussion on concrete mix design. And as I mentioned previously, I'm not really going to go into asphalt mix design only because, again, it's not really covered in the materials, civil engineering materials course here, and it's more covered in a transportation design course. So I'm not going to spend really any time on the mix design aspect. And I don't think there's going to be much in the form of an asphalt mix design question, but there will probably be something regarding performance grade asphalt and the super pay program, which I will talk about a little bit later in this particular presentation. The next thing I want to talk about is the testing methods. Again, these are testing methods that are common to things like steel, concrete, asphalt, aggregate, and again, these are common materials that we use in civil engineering construction. All right, so the first type of test we'll look at will relate to, or look at concrete tests first. The first one is probably one of the most common ones that we see and used for concrete is a slump test. So again, here we have a slump test. We have a frustrum, a cone frustrum here that has certain dimensions that are outlined in ASTM standard. And again, what we're doing is we're filling this cone in 3 equal layers. Each layer is rodded 25 times. Okay, so total number of rods, so to say, is 75 throughout this entire thing. But each layer there's 25 rods. And after you rod it 25 times, you're going to pull the cone up very slowly, about 5 seconds or so, to actually get the whole thing off. And you're measuring from the top of the original cone, originally the frustrum up here, to the peak of that particular slump, or of the concrete after the cone is released. And this distance here is your slump. Okay. So that's how we actually perform a slump test. And again, this gives us some indication of the consistency, or really the workability of the concrete. Okay, so it's kind of a measure of that, indirect measure, so to say, of those particular properties. And it also kind of gives us an indication of, and this is very indirectly, of the amount of water, so to say, in the mix, particularly if you're not using any admixtures, right? So if you have a concrete and you're just using cement, water, and aggregate, no admixtures, and it has a very large slump, probably means that there's going to be a lot of water in that mix, and it's probably not going to have as much strength. So they can give us, in some cases, again, not all cases, but some cases, it can give us maybe a little bit of an indication of what type of strength we might expect as well. All right. So again, I've mentioned this already. We're taking our cone here. We're rod it with a specified rod by ASTM standards. Each layer 25 times. All right. Once it's filled, we remove the concrete from the base. Remove the mold about 5 seconds or so to take it up, and we measure the slump as you see here to the nearest quarter of an inch. All right. So again, we have typically 3 different types of slumps. We have a true slump, which is the kind of the slump we want to see, and that's a good mix. Typically settles fairly gradually, so kind of uniformly. All right, and again, we measure the slump here. We can also see a shear slump, and this is indicating that we don't have a very good mix. The mix is poor. It will crumble. Particles are segregating. All right, so we have larger particles on one side, smaller particles on another side. Basically, we don't have a good mix of particles in there, or the particles are not well mixed within the concrete. So this is not your ideal type of slump. You don't want to really see this. Another type, of course, is a collapse slump. Okay, so again, a collapse slump indicates that we have a very high slump. Concrete basically collapses, and again, if you're not using any admixtures, that might be an indication that you have. Might be an indication that you have a very high water-cement ratio, and probably not going to have very high strength. Now, if you're using some type of water-reducing agents or some type of super plasticizer, whatever it might be, to actually create that high slump, then that's something might be okay. But if you don't use those and you see a high slump, you might be a little bit concerned and say, okay, the strength may not be great. But then again, maybe it will be as well. So I mean, it's not a definite thing, but something to kind of just think about a little bit. Down here, down towards the bottom of the screen, I provided you a link to a YouTube video that just kind of shows the process of performing a slump test. So I'll allow you to look at that if you're interested. That's also something that was covered in a civil engineering materials lab. Two other common tests, or I should say one common test, but there are two different methods of doing it, is the air test. So again, this is a way of actually measuring how much air is in the concrete, what percentage of air, and again, you have an air pot or a volumetric air meter. So air pot is probably the most commonly used method for determining air, and this is used for normal weight and also heavy weight aggregate. Volumetric method is only really used for lightweight aggregate. So if you have very lightweight aggregate, lightweight concrete, you might have to use the volumetric method. And you can see this gentleman here is putting in some isopropyl alcohol, and that's what's commonly used in this rolling meter for determining air content. Okay, but this is the more common method that is used today. And again, there's a couple of different video links here to YouTube that you can take a look at, just kind of showing how both types of methods work. And one of the last things that you often will do on a field site is to actually measure or determine, or not measure, sorry, to form concrete cylinders. All right. So you either take 6x12 or 4x8 cylinders, and you want to make sure that you fill those with concrete. And eventually, you're going to test the 7 and 28-day strength of that particular concrete and determine if it meets the standards required of the concrete. Like I said, 6x12 and 4x8 are the two common size cylinders that you see used. Again, with a cylinder, the height is twice the diameter of the cylinder. The difference is basically in the number of layers that we fill the cylinder. So, not obviously the size is also the difference, but the number of layers is different as well. So, if you're dealing with a 4x8 cylinder, you fill it in 2 equal layers, and you rod each layer 25 times, just like we did with the slump test, in terms of number of rods. And then if you have a 6x12, that's 25 layers, 3 layers 25 times as well. All right, so the number of layers is one more for 6x12 compared to a 4x8. And again, that follows ASTM specification that you see listed here. And again, towards the bottom of your screen, I think that shows you that will take you to kind of showing how cylinders are formed if you need a refresher. All right, so now we formed the cylinders. The cylinders have had a chance to cure and harden. Now what? Well, now we want to test the strength, right? So we have our cylinders, and we want to put it into this load frame here. And once we do that, of course, we just apply a load, and we determine how much load it takes to actually break this particular cylinder. And take that load divided by the area, that'll give us the compressive strength. Okay. So again, that's one of the main purposes that we form the cylinders. Again, is just to eventually test the strength of the concrete. And as we mentioned previously, here's our graph showing the effect that water-cement ratio has on the strength. So the higher the water-cement ratio is, the less the concrete strength is going to be. And again, I put this 0.3 number, indicating that we need to make sure we have at minimum water-cement ratio of about 0.3 in order for full hydration to actually occur. Otherwise, it won't. Okay. All right, this is actually covered in the FE manual, page 61. You'll see that they have a just showing you compressive strength versus water cement ratio, and they also show the effect that air entrainment has on concrete as well. All right, so you can see that if you add air entrainment, you're going to reduce the strength slightly from the concrete that has no air entrainment. Of course, that makes sense. By increasing the air content or entraining the concrete with air, you're creating more void spaces, making it less dense, which typically is going to again lead to less strength. Okay, so this relationship here is covered on page 61 of the FE manual. So just be prepared to see that possibly something asked related to this particular table on the exam. All right, another type of test that you might see is a tensile test. Very rarely will you see a direct tension test done on concrete. It's very difficult to actually grip concrete appropriately in order to pull it and break it. So you don't really see this method done very much, but again, it's basically taking and gluing, so to say, the concrete cylinder here and here, and just pulling it in a direct tension test and measuring the tensile strength that way. Another way is the split test and also the flexural test. All right, so with a splitting test, again, this is covered in ASTM, you're putting a cylinder on its side and you're pushing down on it along the side of the cylinder, and as you do that, you're engaging the Poisson effect of the concrete. All right, so you're compressing it down in this particular direction, and if you're putting compression in this direction, that means from Poisson effect you're having tension created in this particular direction. Okay, so that those tensile stresses that are created along the width, or along the diameter, I should say, of the cylinder cause the cylinder to split right down the center. Okay, so eventually what you'll end up seeing is you end up seeing this thing start to split right down the middle. Okay, so that's the effect that you'll see with a splitting test, and you can calculate the tensile strength of the concrete using a pre-developed formula that you see here. And again, this is not given in the FE manual, so you probably won't be asked to calculate it. But this is, in general, the formula that you would actually need to calculate the tensile strength using the splitting method. Okay. Now, there is an empirical relationship that basically states that through experimental testing, they can determine that the tensile strength is usually between 10 and 15% of the compressive strength. Okay, so that's a good number just to kind of remember, or to kind of know, is that if you have 4,000 psi concrete, you can typically anticipate the tensile strength to be somewhere around 400 psi. So a good rule of thumb is the tensile strength is somewhere around 1/10 of the compressive strength. All right, so we looked at calculating the tensile strength using the splitting test. Another way we can look at determining what's called the modulus of rupture is by actually doing a beam test. All right, so again, we're looking at what is the tensile strength of the concrete, and we're going to apply a beam test, or do a beam test. And in this particular case, I've shown a 4-point load. So we have our reaction forces here, and then the two loads that are being applied, similar to what you see over here. Here's our two rollers up top that are applying a load here and here, and then our reaction forces down here. And as this beam undergoes bending, it undergoes positive moment. Right? So if we were to go ahead and quickly draw the moment diagram for this particular beam, I'll draw it over here. Right? What would that moment diagram look like? Well, it's going to start at 0. It's going to go up like this until we get to that first load of P over 2. Then we're going to see something like this, and then it's going to come down. Okay? So these 2 points that you see here and here correspond to these 2 locations on the beam. And we see that the maximum moment is going to occur in this region here. And if we remember from mechanics of materials that the stress is mc over I, this is the bending stress, right? Then I can calculate what the tensile strength or the tensile stress is on this bottom face of the beam, just knowing this particular equation where m is the moment obtained from the moment diagram, c is the maximum distance from the neutral axis to the point that I'm interested in, or which is going to be, in this case, the very bottom of the beam, which is where the maximum tensile strength is going to be, or tensile stress, excuse me, and I is the moment of inertia of the beam. Okay? So again, this beam undergoes positive bending, which indicates we have something like this. So we have tension on the bottom face compression on the top face, right? And this formula here will allow me to determine what the tensile stress is. Okay, so here's that MC over I equation that I just mentioned. And again, you can easily determine what that moment is by the moment diagram. C is the distance from the, again, the neutral axis to the face that I'm interested in, which again, if it's the bottom, is just going to be half a d. All right, so d over 2. And then I is the moment of inertia, 1/12 bh cubed if we're looking at, bh cubed, if we're looking at a rectangular cross-section. Plug all that into this particular equation and you end up with this as your modulus of rupture. All right, so that'll give me what the stress level is at the bottom of this particular beam. And again, it's somewhere between 10 to 23% of the compressive strength. And there is an empirical relationship here that allows us to see that the modulus of rupture is approximately 12 times the square root of the compressive strength. So oftentimes, we don't have to run, if we're looking for an approximation, so to say, of the strength of, tensile strength of concrete, we can easily just go to these empirical relationships that have been developed, just if we just do one simple compression test or have the compressive stress compression test done and know what the compressive strength is. We could just go to these type of relationships to kind of determine what we expect the tensile strength to be. Okay, so again, these are all based on experimental data that has been developed over time. All right, modulus of elasticity. So that's the next thing here that we want to just kind of keep in mind with concrete. Okay, so we have concrete is a kind of a composite material in that it is made up of aggregate, and then you also have, of course, your cement paste, which is the cement and water. All right, so with the rule of mixtures in play, you have two different constituents coming together to form a composite property or composite material. So the elastic modulus is very much going to be dependent on the elastic modulus of cement plus the elastic modulus of aggregate. All right, so it's kind of going to be a combination of the two. But there are many different ways that you can actually calculate the elastic modulus. And the most common way to actually do it is using what's called the initial tangent method. Right. So the initial tangent method just looks at the initial linear portion of the stress-strain curve. Okay, and if you do that, what you end up seeing is that slope is your elastic modulus. All right, so that's the most common way to do it. There are two other ways as well: the secant modulus method, and there's also the tangent modulus is another way of doing it. But this is the most common way in the way that I would expect that you would do it on an FE exam if you needed to, which again is just looking at the straight linear part of the stress-strain curve here initially and just finding the slope, and that will tell you what the elastic modulus is. Okay. The other thing I'll just mention here is that you have the maximum stress, F prime sub C, that's our compressive strength, that's the peak, of course, of the curve, and then your E sub Cu, that's the ultimate strain. So that's the strain typically when the concrete actually breaks, and most of the time that's somewhere around 0.003. Is the strain level there. So oftentimes if you look in structural design and the ACI codes and things like that, they'll say that the use E sub C equal to 0.003. That 0.003 is basically the failure strain, so to say, of the concrete. All right, so what effect does water content have on workability? Or water content we know affects workability. However, an increase in water without corresponding increase in cement will reduce the strength. So again, related to water-cement ratio, superplasticizers are the most typical method to increase workability. So again, making concrete more workable, it's a lot better to use superplasticizers or water-reducing agents as opposed to just using adding water to the mix, because adding water will reduce the strength. All right. But this particular table just kind of just shows you, one of the reasons why I put it in here, just to kind of show you what effect curing has on concrete. All right, and also what effect time has on concrete. So curing method as well as time. So you can see over time as we reach about 14 days, we've hit quite a bit. We have achieved a lot of our strength within the first 14 days of curing. After that, we gain a little bit more strength, and then things start to kind of level off. All right, and over time the strength continues to increase. But the way it increases is the amount it increases over time reduces significantly after a certain point. Okay, so even after 28 days, we're still going to achieve a little bit more strength than what was at the 28-day mark is just, it's not going to increase a whole lot necessarily, unless we have it in service for maybe a very long period of time. Maybe it will, but it will take a lot more time to gain any strength beyond a certain point. But curing method is also something I want to point out here that's very important, and it's very important to make sure that you cure the concrete appropriately. So when we're curing concrete, we're allowing the concrete to fully hydrate. All right, that's the important thing to keep in mind. We're allowing it to fully hydrate, and that by doing that, what we're doing is we're controlling the temperature and the humidity level of the concrete to keep the moisture in and allow the hydration to fully occur. Well, if you take a look, here's an example of a curve that you might see if you're curing something in open air. All right, so suppose I'm not using burlap sacks, or I'm not using any plastic to kind of keep that moisture in. Then what we see happening here is we see that the strength is not going to be able to fully gain. So we're not going to the concrete's not going to hydrate appropriately to gain the appropriate amount of strength. All right, so it's very important that we have proper methods of curing. And again, moist curing is the best form to do, making sure moisture stays in. And you can see that's this curve here, and that's where we're really gaining the most amount of strength using this particular curing method. Okay, so curing method has a lot to do with, or has a huge effect on the overall final strength and final product, so to say, that we get in the concrete. Okay. All right, so those slides there were really discussing some of the common tests that we see for concrete. Now let's move on to metals, such as steel. All right, so the biggest test that we see used for steel is tension tests. All right. So with this particular test, what we're doing with steel is, again, we're taking this specimen that we have here, our coupon, so to say, and we're pulling on it in tension, seeing how much load it takes to break the specimen. And we plot the stress versus strain. So again, remember that typically these devices here, such as this extensometer, will measure how much displacement undergoes in this particular region. And if I can know that displacement and I know the initial length of this particular region, I can easily calculate the strain. And the stress is just how much load is being applied divided by the cross-sectional area of the specimen. And the cross-sectional area, that's something that we measure prior to actually doing any testing. Right, so we measure that A value, we measure the initial length, and by doing that we can easily use the load and displacement data given from a machine such as this one here to calculate or determine the stress strain properties. And from this we can determine the elastic modulus, of course, of the material, as well as the ultimate strength as well, and also what is the yield point. Okay, so these are some of the common things we get out of the stress strain curve. Now again, we start out here when we see the linear part of the curve. This is the elastic region. So this is where the material is elastic. So if I remove the load anywhere within this particular line, say we're up to 50,000 pounds, and we release the load, then the specimen should go back to zero deformation. Okay, so it remains elastic. Then we are going to eventually hit a yield point where we see that we reach a load that's causing, or I should say we're reaching a point where the deformation continues to increase based on a constant load. All right, so the load's not changing, but the deformation keeps increasing at that particular point. And then something happens within the material at the microstructure level, where the atoms rearrange themselves so that they start to pick back up, and we get what's called strain hardening. Okay, so the material kind of gets its second wind, so to say, after this point, and it starts to harden up to a particular point, and then eventually it goes back down until we get to the point where the material fractures at the end. All right, so the peak point right here, this is the ultimate strength of the material. We just come over here and determine that value of stress. This point here will give us what our yield stress is, and then this point will actually tell us what the failure load was and what the failure strain. So how much strain the steel was able to actually take before it actually broke. Okay. Another type of test that we might see for metals is what's called the brittle hardness test. I only bring this up because it is mentioned in the FE equation packet on page 59. But basically what you're doing here is you're taking your specimen, say this little piece of metal that you have here, all right, and you have some plunger that you see right here, and this plunger is applying some load P, and there's a small metal ball that is used on top of that specimen, and you're applying a force, and you're basically going to measure how much area is indented in the metal below from this particular ball as a result of a load P that's being applied. Okay, so you have this ball that's sitting on your metal specimen, you're pushing it down with some load P, and then based on that load P, you're actually able to calculate, and also the area of indentation, you're able to calculate the brittle hardness number, and that brittle hardness number is directly correlated to the tensile strength. Okay, so I bring this up because if they tell you, for example, okay, the brittle hardness test produced a number of 500, what is the tensile strength? Well, again, you can use this relationship that the tensile strength in PSI is equal to 500 times the brittle number. All right, so if the brittle hardness number is 500, then it's going to be 500 times 500, and that will tell you how many PSI in tensile strength you have. Okay, so it's 500 times the brittle hardness number. If the brittle hardness number is 30, then it's 500 times 30. Okay, and that will tell you approximately what the tensile strength is. The nice thing about a test like this is it's somewhat of a form of a non-destructive test. Even though we're kind of damaging the material a little bit, we don't actually have to break the material in order for determining the test strength of the material. Okay, so that's one of the nice things about a brittle hardness test, is that you can actually measure the properties of the material, and particularly the strength, without actually breaking it, which is something we don't have the luxury of doing with basic direct tension tests on metal. All right, so that was the testing that you see commonly done for metals and steel, things like that. The next thing we'll look at is asphalt testing, in particular penetration penetration testing. Okay, so what you have here is you have a can of asphalt, and keep in mind when we talk about asphalt that temperature plays a huge role in the properties of asphalt. All right, so when asphalt is heated to very high temperatures, it will behave more like a liquid. Okay, and if you have asphalt at lower temperatures, you're going to see it be more of a solid. Okay, so it's important when you're running this test to run the test at some specified temperature under ASTM standards to get an appropriate penetration number, because the temperature of this asphalt is going to affect how much penetration that we get into the asphalt. All right, so you have your can of asphalt that's under some particular temperature. You have a 100-gram mass that sits up here that's attached to a plunger. And what you're doing is you're figuring out how much penetration does this plunger go into the asphalt in a 5-second period of time. Okay, so within that 5-second period of time, you measure that particular distance, and that correlates to your penetration number. Okay, so the higher the penetration number, the weaker the asphalt is, so to say. The less stiff it is, the less hardness it is. So it's much softer, I should say. Maybe that's a better word to use. The higher the penetration number is, the softer the asphalt is. So the more the plunger is able to actually go into the asphalt can. Okay. The lower the penetration number, obviously, the harder the asphalt is. Okay. Going to give us an indication of a little bit into the viscosity as well, because if it's more viscous, then it's going to typically be harder, and it's going to have a smaller penetration number, as opposed to something with a larger penetration number is more liquid and therefore less viscous. Right. All right, and another thing to kind of think about is low temperature cracking. Again, this is part of the SuperPave program, so to say. One of the conclusions that came out of the SuperPave program, which said that when you have very low temperatures, or when you have low temperatures within your asphalt, the asphalt will start to shrink, right? And as it starts to shrink and it becomes more brittle, it'll start to form these cracks. Okay, so cracking is a result of low temperatures in the asphalt. All right, and that's what you're going to see here, is that the asphalt's trying to shrink, it's going to try to pull apart from each other, and again you create this type of cracking. So that's one conclusion of the SuperPave program. Another one was the rutting effect. Okay, so rutting occurs due to high temperature. So at high temperatures, the asphalt binder loses some of its stiffness, and it creates some ruts in the roadway. Okay, so This is probably a better slide showing an example of rutting, but you can see these depressions that are occurring in the roadway surface. Again, these are due to higher temperatures, right? So at higher temperatures, the asphalt binder loses some of its stiffness, and as a result, you see some of this depression that occurs in the roadway. Okay, so again, that's what we see as a result of higher temperatures. And the third, of course, and I don't have a slide for this, maybe I should, but the third main conclusion of the SuperPay program was that you could see some type of spider or alligator type cracks occurring due to fatigue loading. Okay, so due to very high loads on your pavement over and cycles of loads. So these high loads occurring over a long period of time in a repeated fashion, so in a cyclic fashion, you start to see these type of alligator cracks, almost like spider web type cracks that occur in the pavement. All right, so those are really the three main conclusions that came out of the SuperPay program as a result to asphalt type roadway failure. All right, another thing out of the SuperPay program was this performance grade system when it comes to SuperPave asphalt binder specifications. Okay, so you see this particular couple set of numbers listed here and this PG in front of it. So PG stands for performance grade, all right? So performance graded asphalt starts out with a PG, and again, the first number corresponds to the maximum temperature, okay? So the maximum 7-day temperature that we expect the asphalt to experience in degrees Celsius. So in this case, this is 58 degrees C. Would be the maximum temperature we expect of that particular pavement. And the second number is this number here, negative 22 degrees C. Okay, so this is the minimum design pavement temperature. Okay, so the first number is the maximum design pavement temperature in degrees C. The second number, including that negative sign, is the minimum pavement temperature. And PG stands for grade. All right. So if we look at this quick kind of test, so to say, which performance grade asphalt binder should be performed best when we resist thermal cracking? Okay, so again, where does thermal cracking occur, or when does it occur? So remember the first conclusion that we said as part of the SuperPay program was that at low temperatures, asphalt will start to shrink and it will become brittle and crack. Okay, so therefore cracks cracking in this particular case, thermal cracking, occurs due to very low temperatures. So of these particular 4 asphalt binders, which one could withstand the lowest temperature? Well, the answer is this one, right? Because we have negative 34 degrees C. All right, this was negative 22, this is negative 22, this is negative 28, and this is negative 34. So this particular binder has the capability of supporting much lower temperatures than any of these other 3. So therefore, this is our answer. Okay. Now, which binder should be used to resist rutting? So again, where does rutting occur? Rutting occurs at high temperatures, right? So remember, at very high temperatures, we see the asphalt binder start to lose some of its stiffness, and we see those depressions in the roadway. So in this particular case, we're looking for a binder that can support higher temperatures. Okay, so which binder here produces can support the highest temperature? Well, that highest temperature corresponds to the first set of numbers, right? So 82 degrees C, 76 degrees C, 70 degrees C, and 76 degrees C. All right, so the one that handles the highest temperature is going to be the first one, 82 degrees C. Okay, so therefore this is going to be the best binder to prevent rutting of these 4. Okay, so again, that's just how you kind of read this particular system, performance grade. You got the PG performance grade, and then 82, the first number, the maximum design temperature, and the second number here, including the negative sign, the second number here represents the minimum design temperature. Okay, and again, also keeping in mind that thermal cracking is a result of low temperature, rutting is a result of high temperature. Keep those 2 in mind as well. All right, the next thing we'll talk about is the testing that is done on aggregates. All right, so again, there's not a whole lot here to talk about when it comes to testing aggregate, but aggregate is something that is important. We know that it's very much used in concrete. It's also used in asphalt. All right, so it makes up a big component of the of concrete. High percentage of the volume of concrete is aggregate. The high percentage of the volume of asphalt is also aggregate. So the properties of aggregate will play a bigger role in the overall performance. And we could do absorption testing of aggregates. All right, so here's a kind of a procedure that you could follow for doing that. That's outlined in ASTM standards. But soaking aggregate in there and again measuring kind of similar to what you would do when you measure moisture content. Not exactly the same, but very similar process in measuring the absorption. But we can also do strength testing, compressive tests, for example, on aggregate, and we could determine elastic modulus, maximum strength, and things like that. Just like we would do for something like, say, concrete, for example. Just compressive strength, or determine what is the elastic modulus of the aggregate and the compressive strength of the aggregate. Okay. Some of the things that we can do for aggregates as well. The next thing I'll talk about are some of the properties of aggregates. Right. So again, as I just mentioned here, and as you've mentioned in a materials class, is that materials like concrete and asphalt have a high percentage of their volume or total volume is made of aggregate. All right. So understanding some of the properties of that aggregate is also very important. So durability of the aggregate. How durable is the aggregate that we're using? How porous is it, right? So the porosity relates a lot also to the absorption of the aggregate. And we've talked about what effect, especially in concrete, absorption of aggregate has on the overall properties of that concrete. Okay, so it's important to know the porosity and the absorption, as well as the density. So how much does it weigh? How dense is it? And typically, the more dense the aggregate is, typically the stronger it is. And oftentimes, we're going to see a little bit stronger concrete or asphalt mix when we're using a more dense aggregate. Oftentimes, I'm not saying always, but oftentimes that's what we're going to see. Okay, so just understanding some of these properties of aggregate are very helpful and important to know. All right, again, we can measure specific gravity of aggregate. Again, the density of the material to the density of water, or the specific weight of the material to the specific weight of water. Either way, we can calculate specific gravity. Moisture content is just the weight of the water divided by the dry weight of the particular aggregate. So if you're given, for example, an original weight that of some aggregate that contains moisture, and then you put it in an oven and dry it overnight or whatever, and you get the oven dry weight, then the difference between the two will give you how much moisture you have. Divide that by the dry weight to get the total moisture content. Okay. Absorbed and surface moisture. So absorbed moisture is basically moisture that's within the pore space of the aggregate. All right, so the little miniature pore spaces that we can't see really with the naked eye that exist in the aggregate, any moisture within there is absorbed moisture. Any moisture that may be on the surface of the aggregate is called surface moisture. So some technical terms, so to say. Surface dry, that's basically when we see the pore spaces of the aggregate are completely filled with fluid, or completely filled with, say, water, but the surface is dry. Okay, so all those little micropores within the aggregate have water filled in it, or they're filled with water, and the surface of the aggregate is dry. We can calculate the absorption of the aggregate if we just can calculate if we know the surface dry weight minus the oven dry weight divided by the oven dry weight. That'll tell me what the absorption of the aggregate is. And then finally, surface moisture is just the difference between moisture content and the absorption. Okay, so again, just some things to just kind of keep in mind. All right, engineering problems. So again, this is probably more along the lines of something that you could see for the FE exam in relation to some problems are really what are the properties of metals, engineering properties of metals. In particular, if we give you a stress strain curve, can you point out the yield point? Can you point out the ultimate strength? Can you point out the yield strain? Can you determine the elastic modulus? Things like that. That's really, I think, a big part of things that could be asked on an FE exam is really what are the different properties of metal if you're looking at the stress strain curve, right? So again, the yield point, we have an elastic limit and proportional limit, which I define here. But more commonly, the yield point is something that's very common to talk about or to look at. And again, that's a point where the strain the stress remains constant while the strain increases. All right, so that's where we see the yield point here, and again that will give me the yield stress over here, and then we come down to this axis to give us the yield strain. Now in certain cases, which I think I'll show on the next slide, so I don't want to get too far ahead of myself, so I'll talk about that in just a second, but in certain cases it might not be so clear on a stress strain curve where the yield point occurs. So we might need to use what's called the 0.2% offset method in determining that, and I'll go over that in just a second on the next slide, because that is shown in the FE equation packet, and I just want to bring that up to your attention. All right, the ultimate strength, that is the peak stress that you see in the stress strain curve. Brittle versus ductile material, the difference between the two. Again, when we talk about a brittle material, we're saying that's something that does not undergo very much deformation prior to fracturing. So, for example, concrete is a good example by itself as a brittle material. Glass is a brittle material, so you have very small deformations prior to it actually fracturing. Whereas steel can undergo, as you see out here, for example, can undergo much larger deformations before it fractures as opposed to something that's more brittle. Okay. And toughness is just defined as the area underneath the stress strain curve. So the greater the area under the curve, the more the toughness is. And again, these are just something that easily to ask on an FE question. Two stress strain curves. Which one has which material is tougher? Which material is brittle versus ductile? So on. So all easy things to keep in mind, or to ask, I should say. Another thing I want to point out is the effect that carbon has on metal. This is probably one of the biggest things to take away from any topic on metal and the properties, is that the effect that carbon has on it. So the higher the amount of carbon, typically the higher the strength, or not typically, the higher the strength the metal is going to have. All right, so if you have a higher carbon content, you're going to have greater strength. However, when you add carbon, you increase strength, but you decrease the ductility. Okay, so the ductility of the carbon, or the steel, or the metal, reduces significantly as the carbon content increases. All right, so there's a little bit of a trade-off with carbon content, that it helps with strength, but it decreases in any type of ductility. And that ductility might be something that's very important in your design application. So you want to make sure you kind of keep that in mind. All right, so I mentioned previously about the 0.2% offset method. So in certain cases, such as this particular stress strain curve, you can see there's not necessarily a clear point where you see that the stress remains constant while the strain is increasing. So oftentimes you might have to use what's called the 0.2% offset method. So remember, 0.2% is 0.002 strain. Okay. So what you would do is you would go to the 0.002 strain value on the diagram, and you would draw a slope, or a line that is the same slope as this initial linear line that you see over here. Okay. So this slope here and this slope here should match. And where this intersects the stress strain curve is the yield point. Okay, so this is where we see, this would be my yield stress, and down here this would be my yield strain. Okay, so this is how we use the 0.2% offset method. And again, I bring this up because it is covered in the FE manual, so just again make sure that you go through and understand how to use this method, just in case it is asked on the FE exam. So again, you're looking at, okay, you have 0.002 strain, drawn a line that has the same slope as this line, and where it intersects is your yield point. All right, we talked about brittle versus ductile materials, and you can kind of see the failure of both. So these are specimens that failed in a direct tension test. And again, you can see the effect that the carbon content, and also the fact that ductility versus a ductile versus brittle material has on the fracture planes. Okay, so if you think back to mechanics and materials, a material that is more brittle, that fails in tension, remember, fails on the 90-degree plane, so to say. So in other words, the failure plane is flat. All right, so we see a fairly flat surface here under a direct tension test for a brittle material, or a material that's more brittle, I should say, versus a material that is more ductile. We see more of a 45-degree fracture plane. Okay, so materials that are ductile undergoing direct tension tests typically fail on a 45-degree plane, as opposed to materials that are brittle typically fail on the 90-degree or a flat plane. Okay, so the fracture zones, as you can see here, will tell us a lot about a ductile versus brittle material. The other thing you notice in this ductile material is that when it failed, or prior to it failing, it underwent some what's called necking. Okay, so you can kind of see in this particular region here and here some permanent deformation that occurred, and some of the the cross section kind of slendered down a little bit. Okay, and it went from an initial say width like you see here down to a smaller width up here. So it kind of necked, as we like to say, at this particular point. So that's very common also to see in a ductile material versus a brittle material, where you don't really see that necking behavior actually occurring. The cross section remains pretty much the same size as it did prior to it reaching the failure point. All right, another thing to point out is that there are tables in the FE equation packet. This is on page 80 of the packet that just give you some properties of different metals. All right, so keep this in mind. You might be asked a question that requires you to know something about the properties of a metal, whether it's the density or the elastic modulus. And if that's the case, make sure you recognize that there's a table for that in the FE packet, and this is the table that you will see. All right, so here's a problem for us, and this is kind of a problem that could be either, could really either correspond to a materials type problem, or civil engineering material problem, or to a mechanics and materials problem. So we'll go over this in just a second, or right now I should say. But we have a steel rail. It was installed at a temperature of 5 degrees C. We're told the length and the cross-sectional area of the rail. And the rail was installed without any allowance for expansion. All right. So in other words, there was no allowance for it to actually expand freely without it touching another piece of the rail or another part of the rail. So in other words, when one rail expands, it would push into another rail. Okay. The ends were constrained by adjacent rails. Okay. The coefficient of expansion for the rail is 11.7 times 10 to the 6 per degree C. What is the compressive force in the rail at 25 degrees C? All right, so to do this, we have to kind of go back to a little bit of mechanics materials, and again, we're going to look at what is the thermal strain that's going to be generated. So again, what is the strain that's generated as a result of that temperature change? Okay, so we know the coefficient of thermal expansion. At 25 degrees C, we have our current temperature. The temperature that it was placed in this particular position was at 5 degrees C, so the change in temperature has been 20 degrees C. Okay, so over that 20 degrees C, we're going to see a strain of 2.34 times 10 to the negative fourth. Okay, so that's the strain in the rail. All right, and we can look up on the FE equation packet, again on page 80, where we had properties of materials, and we look up steel, and the elastic modulus of steel is 200 times 10 to the ninth pascals. And stress, we remember from Hooke's law, again, which is in the FE equation packet, is just strain times elastic modulus, which we get here, and this would be our stress. And the force, therefore, is just going to be stress times area, so I calculate my stress and I get to the force. Okay, and we get 280 kilonewtons. Okay, so that's how much force is being exerted on that particular rail. Okay, so it's really a little bit more of mechanics and materials, but it does require us to know a little bit about the material properties as it relates to the stiffness, in particular, the elastic modulus, I should say, of the steel. All right, but Hooke's law, this basic stress equation here for axial stress and thermal strain, these are all covered again in the mechanics and materials section of the FE equation packet for you to review. All right, so the next question we have here is we have told that the stress in a solid tension member is 324,056 kilopascals at failure. And at failure, the area is reduced by 80%, so what is the actual true stress? Okay, so this is just something to kind of keep in mind when we're talking about engineering stress and strain versus true stress and strain, right? So what is the difference between the two? When we talk about engineering stress and strain, particularly engineering stress, I guess we'll say, basically we're calculating the stress based on a constant cross-section. So we're not really accounting for the change in the cross-sectional diameter or the shape, cross-sectional shape as load is being applied. And we know from a Poisson effect that as we pull on something, say in tension, we know that it elongates, but it also, the width gets smaller. Okay, so there is a change in the cross-sectional area that we're not accounting for as we plot the stress-strain curve, right? So that's something that's important to keep in mind, and that little bit of change in area has some effect on the actual true accuracy, so to say, of the stress value. But for engineering stress, we typically don't measure that change in cross-section on every load increment. And by not doing that, we call it engineering stress as opposed to true stress. Okay, so at 100%, at 100% area, we know that the stress is 324,056 kilopascals, which is equal to force divided by area. Okay, and when the area is reduced by 80%, the new area is 0.2A. Okay. So what is the new stress? So what is the stress at 80% reduction? Okay, so the stress at 100% area is this. At 80% area, the new area is 0.2 times the initial area, okay, of A. So again, we just plug it in here, and instead of putting A, we'll put 0.2A, and we solve, and we get 1.6 megapascals. All right. So again, just another kind of use of engineering mechanics materials to calculate the true stress as opposed to just the engineering stress. All right, properties of wood. So again, when we're looking at wood here, two of the most important properties of wood that can be related to strength, stiffness of wood are the moisture content and the specific gravity. These are probably the two most important physical properties that we have in wood, because again, they can be related to the strength properties and such and durability properties of wood. So again, moisture content, we can calculate just the weight of water divided by the oven dry weight. And if we think about moisture content for a tree, that's typically, again, these values will change depending on the species of the tree and things like that. But on average, it's somewhere around 200%. So there's actually a lot of water that's in a tree. And that shouldn't obviously be a surprise to anybody. But for a lot of most trees, there's a lot of water in there. And it's actually, based on this, it's actually saying that there's twice the amount of water as opposed to actually solid weight, so to say, solid mass in there. And again, that's just an average number. It varies based on tree types or species and things like that. So, and again, there's just some examples here of different types of trees and their water content. So white oak, for example, much smaller moisture content than what we had up here, so 78%. But something like balsa, for example, has a moisture content of 400%. So again, it really does depend. And then you have something like a white ash and a black ironwood. These are really low moisture contents. These are something that are very dense wood, and in fact, these actually have a density higher than that of water. So this type of wood actually doesn't float; it actually would sink. Whereas most wood has a much lighter specific weight, so it actually floats in water as opposed to sinking. All right, so again, moisture content. Water's in the cavity are the first to go, and then in the cell wall. So if these are the cells of the wood, all right, so we have our cell cavities in here, and we have the cell wall around them. Okay, so what's going to happen is as this particular wood takes on moisture, the moisture is going to fill up the cell walls first, and once the cell walls are completely saturated, all the void spaces are filled with water, then the excess is going to start to flow into this cavity of the cell. Okay, and the opposite is going to happen when the water is released. So as the wood is starting to dry out, the moisture is going to leave the cavity first, and then it's going to start to leave the cell wall. Okay, so when we're talking about moisture content, the two that come to mind for wood are fiber saturation point and equilibrium moisture content. All right, so fiber saturation point is perhaps the more important of the two. And basically, when we say fiber saturation point, what we're saying is that the cell cavities, the cell walls, my apologies, the cell walls are completely filled with moisture. So in other words, all the void spaces within the cell wall have water in them. but the cell cavity is completely empty. Okay, so the cell walls are saturated with water, and the cavity of the cell is empty. That is what defines a fiber saturation point. All right. And for most woods, that value is typically somewhere between 25 and 30%. Okay, so when the wood hits a moisture content of somewhere between 25 and 30%, that's when we're actually achieving the fiber saturation point. So the fiber saturation point is a moisture content. All right, that's something that's very important to keep in mind. It is a moisture content. So when we're hitting 25 to 30% moisture content, we can pretty much assume that the cell walls are completely saturated with water and there's nothing in the cell cavities. Equilibrium moisture content is a moisture content below the fiber saturation point. All right? So it is a moisture content below the fiber saturation point, and it depends heavily on temperature and humidity. Okay? So it's a function of those particular variables. So what this basically means is that at a temperature below fiber saturation point, a moisture content below fiber saturation point, all right, for a given temperature and a given relative humidity, that moisture content is not going to change. Okay? So in other words, if I have a temperature of 40 degrees Fahrenheit, and maybe I have a relative humidity level of 50%, okay, again, just making up some numbers here, then eventually I'm going to achieve a moisture content where it's not going to change based on those two values. Okay, it's going to remain constant. So the moisture. So if we have, again, 40 degrees Celsius and 50% relative humidity, again making some numbers up, right? Then that moisture content is going to bump around, and eventually it's going to start to settle out, and it's going to say settle at 15% moisture. Okay, once it settles at that 15% moisture content for that temperature and that humidity level, that is a moisture content that's now in equilibrium. All right, so it's not moving. All right, so it's a constant value that is being obtained at that particular temperature and humidity level. Now, as the temperature and humidity change, the moisture content is now going to change. All right, so again, now at a different temperature and a different humidity level, we might hit a different moisture content. All right, so that's really what equilibrium moisture content is. It's a moisture content that we reach equilibrium at for a particular temperature and humidity level. All right, so reason why we say that moisture content has a big effect on the properties of wood, we've seen that if you have a moisture content that is above the fiber saturation point, so fiber saturation point again is somewhere between 25 and 30% moisture. If we have a moisture content above that, say 40%, all right, then there's no real difference in strength and stiffness in the wood. All right, so in other words, any moisture, as the moisture content increases above the fiber saturation point, the strength and stiffness properties of the wood don't really change. Okay, so as I go from 30% moisture to 50% moisture, the strength and stiffness remains the same. It's not really changing much. Okay, it's pretty much constant. However, if you go the other way and you say take a moisture content at say 25%, right, as your fiber saturation point, and you're going down to say 20%, well, that decrease in moisture content will help increase the strength. Okay, so you're going to see an increase in the strength of the wood as the moisture content decreases below the fiber saturation point, but you're also going to start to see shrinkage develop. Okay, so again, keep in mind what's happening here. Fiber saturation point we defined previously as the point where the cell cavities are empty and the cell walls are completely saturated with water. Okay, so as the moisture content reduces below the fiber saturation point, now we're getting some of that water to leave the cell walls, and as it leaves the cell walls, it's going to start to shrink the wood. Okay, it's going to start to shrink. Okay, so that's what's happening there. Now above the fiber saturation point, right? If you're looking at, say, you have your let's draw out here for a quick second. All right. So suppose we'll just look at one cell right now. All right, and suppose we have. Let me draw this here for a quick second. Alright, so here is this is the cell cavity, okay, right here. And this on the outside here is a cell wall, okay. So at the point that we reach fiber saturation, we know that this entire area, right, is filled with water, okay, or it's saturated, I should say. So all the void spaces in this area are filled with water, okay. But the cavity is empty, okay. So as I add water, as the moisture content increases above the fiber saturation point, where is this extra water going? It's going into the cell cavity, okay. Now what happens if I go from a moisture content of say 50% down to 30%? What's going to happen? Where's the moisture leaving? It's leaving the cell cavity, right? So it's going to leave the cell cavity, and that's not going to change the volume of the wood, because I'm just going to basically be taking an empty space that had water in it, and I'm removing the water from that empty space, but the volume is still the same in here. It's not changing, okay? So when you have a moisture content change from a point above the fiber saturation point to the fiber saturation point, okay, so somewhere between the two, you're not going to see a change in the dimension properties of the wood. It's only when you're decreasing the moisture content below the fiber saturation point that you're going to start to see shrinkage in the wood. So now that I say again our fiber saturation point is 25%, okay, and now I'm decreasing it and the moisture content decreases to 20%, well, some of that moisture is going to be leaving the is going to start leaving the cell walls, right? So now some of that moisture is going to be leaving out of this particular area right here. So this is actually going to start to cause this whole cell to start to shrink, and you're going to start to see a volume change, okay? So as the moisture content decreases below the fiber saturation point, all right, so again, as we're going from, say, 25 to 20% or 25 to 10%, or even going from 20% to 10%, all right, the elastic modulus will increase, the moment of inertia will decrease because the wood is shrinking, and as a result, if we're looking at bending stiffness, which is E times I, if E increases and I decreases, they kind of offset each other a little bit, and you don't really see a big change in the overall bending stiffness of the wood. All right. If you look at axial stiffness, you would have E times A, and again, that would be very similar. The area decreases, the elastic modulus increases, so the axial rigidity also wouldn't change all that much either. Okay. But so that's related to the stiffness of the wood. All right, so again, all properties of wood, physical, mechanical properties, dimensional properties, these are all affected by moisture content. So that's why it's one of the more important properties of that. All right, the next one here is specific gravity of wood. All right, so when we look at specific gravity, again, in the United States, the way we calculate specific gravity is to use the oven dry weight and not the actual total weight or the wet weight of the wood. So the specific gravity for wood is calculated as the oven dry weight divided by the volume of the wood, which we call green volume, and that's just basically the same thing as saying the dry unit weight. Either one, but that's just the way we calculate it here in the U.S. All right, and this gamma value relates to porosity and also void content of the wood. Terminology here, when we say green wood, so this is typically deals with fresh cut lumber. So fresh cut lumber typically has more moisture in it than after we dry the wood, whether it's oven dry or air dry. That's where we're reducing the moisture content significantly. So this is just some terminology here, and of course the specific weight or the weight of the wood is going to depend on things like the species of the tree, the moisture content in the wood, also the part of the tree that the material or the piece of wood is coming from. So whether it's the sapwood or the heartwood, those will have an effect on the weight of the tree as well. All right, so there are some nice tables in textbooks and things like that. These don't actually appear in the FE manual, but there are some tables that you can see that will, for different species of wood, you can kind of see what the specific gravity of that particular wood is, whether it's in the green state, which is fresh cut, higher moisture content, versus oven dry, which is no moisture at all, and you can see the effect that that moisture content has on specific gravity. And you can see here that at higher specific gravities are for when you have less moisture, and the more moisture you have, the smaller the specific gravity is going to be. Okay. There's also this equation here, again, not in the FE packet, but something that just to kind of keep in mind, that there is an equation to actually calculate the unit weight of the wood if you have some idea of the moisture content, as well as the specific gravity, oven dry specific gravity of the wood. All right. The other thing here, and this is at the bottom, this is perhaps the most important thing on the slide, is that the specific gravity does affect things like strength and stiffness. So the strength will increase as well as the stiffness when the specific gravity increases in the wood. All right, simple calculation problem here. You have a moisture content, you have some dimensions given. Calculate the specific gravity. All right, so again, in this particular case, again, recall here in the U.S. we use the dry weight when we're calculating a unit weight of wood. So I need to make sure I'm using the oven dry weight, which is 0.55 pounds in this particular case. And then I want to divide it by the specific weight of water, which is 62.4 pounds per cubic foot. That's always a good number to kind of memorize for water. It's 9,800 newtons per meter cubed in the SI system. Yeah. And this is the dimensions, right? So the big thing to just kind of remember are units here. So again, the pounds per cubic foot, this is per cubic foot. These are in inches cubed, so you have to make sure you convert something. And if you do that, you get 0.51. So the specific gravity of this particular wood is 0.51. All right, loading wood. This is also something that's very important. So what are the different failure modes that we see in wood? All right, so there are many different ones that we can see. We have tension parallel to the grain, compression parallel to the grain, compression perpendicular to the grain, and we also have shear failure parallel to the grain. So these are really the main modes of failure that we would see in PCB. Modulus of elasticity, again, the direction of the fiber of the wood. So the cells are actually the fibers. That's what actually gives strength and stiffness to the wood. The direction of those particular fibers have a direct impact on the overall strength and stiffness. Okay? So anytime you're looking at the strength or stiffness with the fibers, that's typically going to be much higher than anything against the fibers or perpendicular to the fibers. Right? So the modulus of elasticity is greatest in the direction of the fibers. All right, and if you look at it, it's somewhere between 1 million and 2 million psi as the elastic modulus. Compare that to steel and concrete, it's much lower. So wood is typically not as stiff as concrete and steel is. Another thing to keep in mind is that moisture content is very important. All right, so when we come to the elastic modulus of the material, the elastic modulus will decrease as the moisture content level increases. Okay, so the E value will drop whenever the moisture content goes up, provided that the moisture content is below the fiber saturation point. Okay, so if the fiber saturation point is, say, 25% moisture content, then as I am going from, say, 10% to 20% moisture, then I'm going to see a decrease in the E value, elastic modulus. However, if I'm going from, say, 35% moisture content to 40% moisture content, there is no change in the elastic modulus because we're looking at now two moisture contents that are above the fiber saturation point. All right, compressive strength parallel to the grain. This is something that's very commonly seen for wood, particularly if you're looking at posts posts or timbers. These are commonly things that are in pure compression. Again, if the grain of the wood is running in this particular direction, then we're talking about loading that is occurring parallel to the grain or with the grain, as shown. For softwoods, which are primarily the type of wood that is used in civil engineering construction, for structural members at least, we're looking at 2,000 to 4,000 psi. All right, so compressive strength is not that bad. It has a very good strength to weight ratio, which makes wood a good material to use. But when you do compare it to other materials like concrete and steel, it's not quite as high. But in terms of strength to weight ratio, it's very good. Another thing you might see a failure would be compression perpendicular to the grain. So a good example of this is if I have a girder and then I have a floor joist that rests on top of it, as you see over here, then this point here where the joist intersects or is in contact with the wood is creating a compressive force that's perpendicular to the direction of the grain. Okay, so you're going to create some type of a indentation, so to say, around this particular point. All right, so you're going to see some type of a lateral collapse of the fibers as a result of that compressive force. And if you look down here, that compression perpendicular to the grain is somewhere between 12 and 18% of the overall strength parallel to the grain. Okay, so if you have 1,000 psi as your compressive strength parallel to the grain, then perpendicular to the grain is probably going to be somewhere between 120 and 180 psi perpendicular. All right, so again, as we mentioned previously, just like before, as the moisture content increases below the fiber saturation point, the compressive strength will decrease. All right, same type of principle as we saw previously with elastic modulus that we talked about. So another thing, this is another reason why it's important to dry the wood first. So if you can have drier wood in the construction, then you're going to have better strength. All right, so this is one advantage of seasoning, as you say, wood. Another type we see here is the flexural strength or the bending strength of the wood. Not used as much as a property only because wood starts to become more inelastic as the load increases. In fact, it's really only elastic for small loads. And once we get above or beyond this elastic limit, we start to see some nonlinear behavior. And as a result, this equation that we have here for modulus of rupture, the my over I equation, is only valid when the wood remains elastic. So if it starts to become more linear elastic, or inelastic, I should say, excuse me, not linear elastic, but just in nonlinear behavior, then this particular equation is not valid. So it becomes more of an error to be used. But wood is something that is very commonly used as flexural members, right? It's very commonly used as beams, for example. All right. So another thing to kind of look at is, again, what effect the specific gravity has on the modulus of rupture. And if, again, you take a look at the bending strength here, wood that is air dry, so with less moisture content, the modulus of rupture increases as opposed to something that has a higher moisture content, excuse me. And again, you can see here as the specific gravity increases, so too does the modulus of rupture. All right, and here's another graph here again showing the effect of moisture content on different stresses. So if you're looking at compressive stress parallel to the grain, right, as the moisture content increases, the compressive strength will decrease, as we said, up till we hit the fiber saturation point. Okay, so this is about the fiber saturation point for this particular plot, and you can see once we hit past that fiber saturation point, it starts to level off. Okay, so again, as the moisture content increases above the fiber saturation point, we no longer will see a decrease in the compressive strength. It will just level off. Okay, same with the modulus of rupture, and also the same with the modulus of elasticity. The modulus of elasticity, you can see the slope is not as great as it is with modulus of rupture and the compressive strength. All right, so the effect of moisture content is not as high on this particular parameter as it is on these two, as you see here. The next one here is tensile strength perpendicular to the grain. Okay, so perpendicular to the grain, you just want to avoid it. It's about 0. All right, so really what you're doing when you're applying a load that's perpendicular to the grain, you're applying it against the fibers, and really what you're doing is you're just pulling against the glue that's holding the fibers together. Okay, so the glue that's holding the fibers together is what's referred to as the lignin. All right, so you're pulling the lignin apart and when you're applying a load that's perpendicular to the grain as such. And the lignin does have some tensile strength, but it's very small. It's not very high at all, so we usually just approximate it to be 0. So in practice, you just want to avoid designing using a piece of wood that has a load that's in tension perpendicular to the grain. All right, so we always assume it's about 0. However, tension parallel to the grain is very good. You can see it's actually 2 to 4 times the compressive strength parallel to the grain. So compressive strength parallel to the grain, we said before, was somewhere between 2 and 4,000 psi for softwoods. Right, so this is somewhere between 2 to 4 times those values, so pretty good strength to weight ratio again. But again, when you're comparing it to something like steel, not even close, right? Steel has very high tensile strength properties. However, concrete is very low, right? And the tensile strength of concrete is highly dependent on the compressive strength. So again, remember the rule of thumb that we said earlier, the tensile strength is approximately 1/10 of the compressive strength. So if you have compressive strength of 4,000 psi, the tensile strength is going to be about 400 psi. Okay, so the tensile strength of wood is much greater than that of concrete. All right, so but again, this is just plain concrete, not reinforced concrete, right? So just again, something else just to keep in mind there. And we have shear failure that occurs parallel to the grain. So again, if you're having a beam, you apply a load here and you're looking at the shear stresses in this particular region. Remember, shear stresses is calculated using this particular equation from the mechanics of materials section of the text of the FE packet. All right. And again, you have horizontal shear stresses that occur as well as vertical shear stresses within the wood. And typically, the one that's actually going to fail first is the force, I should say, or it's going to fail first in shear that occurs parallel to the grain as opposed to perpendicular to the grain. Right. So again, something else to just keep in mind here is that when we're drawing this out, it's very easy for us to see. If I draw out this stress block, come down here for just a quick second. Right, it's very easy for us to notice that, okay, I have a load that's going up this way from this guy, and then I have a load that's going down this way that we see from this particular guy. But this block by itself is not in equilibrium. All right, so in order for this thing to be in equilibrium, just kind of have to keep in mind that if we have this arrow and this arrow causing a clockwise rotation, then this arrow and this arrow have to produce counterclockwise to balance them out, right? So that's why we see something that looks like this. And it just kind of again shows us that, yes, we have some vertical shear, but we also have horizontal shear that occurs in the beam. And it is that horizontal shear that actually is going to fail prior to this vertical shear actually causing failure. Okay, so this is what we actually are interested in. Of course, these shear stresses are the same values anyway, but we're just trying to look at and find what is the shear stress is going to cause this to fail. And basically split in these areas right here. Okay, so again, it's going to occur in these regions because these are areas that have shear force or shear forces. All right, so if you drew the shear moment, or if you drew the shear diagram for this particular load case, you would notice that there's shear in this region and there's also shear in this region. Okay, so wherever we see maximum shear is probably where we're going to see shear failure occurring, because this is where the highest shear force is occurring. Okay, so the highest shear force is going to produce the highest shear stress. Right. All right, and the final engineering property that we'll talk about is that of masonry. All right, so the last material here again is masonry, and again, the tensile bond strength is the most important part of any masonry construction. It is the bond strength that keeps everything together. It holds the entire wall together, so to say. If the bond deteriorates, then we don't have the masonry units acting with each other, and therefore the wall loses its strength and integrity and will fail. So tensile bond strength is the most important. But we also want to keep in mind when we're talking about the mortar, which is, again, what keeps the units together, workability and durability are also very important as well. So how easy is it to actually place the mortar where it needs to be, and also how durable is it? Can it withstand things like freeze thaw and and other environmental effects? And sometimes you have to add air to help improve durability, similar to what we did when we talked about concrete. All right, density, when we're talking about first clay bricks, so clay brick, you can see the density here. Absorption is a big player when it comes to clay brick. Clay is very absorbent material. It wants to take in a lot of water, all right, so it's something that's very important just to kind of keep in mind. Like I said, it does affect the durability, affects the bond strength, and in particular, when we're talking about absorption, initial rate of absorption is something that's very key to keep in mind, because initial rate of absorption is basically the absorption that the masonry unit is going to take from the mortar. Okay, so the mortar is very similar to concrete. All right, in that mortar needs to fully hydrate in order for it to gain its strength. All right, and to hydrate, it needs water. And if you have a masonry unit that's going to take the water out of that mortar mix, then what's going to happen? It's not going to be able to fully hydrate, and that's going to be a big problem. Okay, so it is important to make sure that we maintain good water within the mortar mix so it actually fully hydrates and gains the full strength. So it's important to measure the initial rate of absorption of a masonry unit, and this is how you'd actually go about measuring that initial rate of absorption. Absorption by itself is a big player as well, because if you have water that the masonry unit takes on a lot of moisture from the surrounding environment, and it stores in a lot of that water, and then eventually it freezes, you can create some deterioration due to freeze-thaw effects. Okay, so again, keeping in mind absorption is a very big player when it comes to understanding the properties of masonry units. In fact, absorption and strength are the two main properties that classify, or are most important, I should say, when it comes to masonry units. Strength, here's the second thing. So with strength, again, it's similar to when you're actually measuring the compressive strength of, say, a concrete specimen. You're just applying a load to that particular masonry unit, and take that load divided by some area, and that will tell you what the actual compressive strength of the masonry unit is, whether it's clay or concrete unit. Okay. The big thing here is just to kind of keep in mind this A net. This is the net area, and it really depends. So when you have your masonry unit, this is, say, a top view of that unit, and you have the two, maybe you have a couple of core spaces or cavities in that particular unit. All right, so the gross area, or sorry, the net area is basically all the area that does not include the empty cavities, right? So that's the gross area, and the net area is the entire thing, the whole area including the empty cavities. Okay, so if the gross area, or sorry, the net area is more than 75% of the gross area, I'm going to use the gross area in this equation. Okay, if not, I'm just going to use the net area in blue. Okay, so this is just something to keep in mind when you're calculating compressive strength. All right, again, you have some properties here of clay masonry brick: modulus elasticity, thermal expansion properties, other good features of brick. I'll let you go ahead and those. Expansion, again, is something that's very important to think about and keep in mind, especially when it comes to clay units, because clay is very susceptible to swelling when it takes on water. So it does like to take on a lot of water, and it will swell up, and as a result, it does expand. But in addition, it expands and contracts due to temperature as well. So anytime you're dealing with clay units, it's important to make sure you account for any expansion that can occur due to an intake in moisture as well as due to a temperature change. With concrete, it's a little bit different. Concrete is not as susceptible to water as much as clay is. So it doesn't swell like clay does when it takes in water. So as a result, we don't really have a moisture coefficient that we have with clay. We just have a temperature coefficient. All right, so I can actually calculate how much expansion and contraction a masonry wall will undergo. If I know those two coefficients, I know a change in temperature, and I know the length between expansion and contraction joints in a wall. Okay. All right, compressive strength. So again, the compressive strength is dependent primarily on two different things. Number one, the compressive strength of the individual masonry unit, and also the type of mortar that's being used. So when we're saying on masonry, we're not just now, at this point, we're not saying just a masonry unit, we're saying masonry system. So the masonry system is both the masonry unit plus the mortar, and possibly any grout that's being used as well. Okay, so that's what we mean when we say masonry. Masonry is a combination of the unit plus the mortar. All right, so the actual strength of that particular system is going to be a combination of, which is given as F prime sub m, is a combination of the compressive strength of an individual unit and the mortar strength, the type of mortar that's being used. Okay, so depending on the type of mortar, that will give us, and this will also give us the strength of the masonry. And you can see some of the things that it depends on, but the big one I highlight here in red is always workmanship. We kind of don't think about that, in that somebody who is a trained mason who's been doing it for many, many years is going to do a much better job than somebody that is not as trained and doesn't have as much experience. So that workmanship is obviously also going to affect the strength, so something to keep in mind. This is how we actually go about determining the compressive strength of masonry. So we create these prisms, all right? So they are at least 2 bricks high, sometimes 3, 4, 5 units high, and we just form them up in a single layer, as you see here, all right? And then we're going to put it in a machine and test it in compression to see what the actual strength is. And that actual strength we get in the machine is our F prime sub m that we saw in the previous slide. So F prime sub m is the strength of this entire masonry prism, or the masonry construction. Whereas the value that you saw previously on the x-axis is the strength of an individual unit. And then we have the mortar in between here, which has, depending on the type, has different strength values. Alright, so elastic modulus is another property of masonry construction that has some things that it depends on. And again, typically what we see is that with higher compressive strength, the elastic modulus is higher. And as the mortar strength increases, the elastic modulus also increases. So this is a couple of things that have been noticed, again, as you go through things like that. Thermal conductivity. All right, thermal conductivity is something also that is kind of important to just kind of think about, and this relates to the time rate of heat flow through a unit area. So in other words, how good of insulation, so to say, is the masonry? How good does it do in keeping the temperature from one side of the wall from going to the other side? All right. So this is in some cases it's good, in some other cases it's not as good. But the thermal conductivity increases with density and moisture content. All right. So that's something also to kind of keep in mind there. Heat transfer is another thing. Again, heat transfer depends on the temperature between the two sides of the wall. We had 3 different methods of heat transfer. We had movement and mixing of molecules, gases, liquids. That's convection process. And then we have radiation. And then the last one is conduction. So conduction is basically transferring heat from one area to another area by contacting other particles, adjacent molecules or particles next to it. So you have multiple molecules. You have a molecule here touching another molecule, touching another molecule. I don't have a great stylus here, but okay. So you have all these molecules, and they're just going to the heat's going to transfer across by with conduction by just touching each of them and just transferring as they go. Okay, so this contact, point-to-point contact, basically, is the method of heat transfer. Now there is an R value that you a lot of times will see in construction, which again relates to how good the insulation is for that particular construction. And the higher the R value, typically the better the insulation. So in other words, the higher the R value, the more difficult it is for temperature to cross the barrier between that insulation. So a higher R value is better than a lower R value. So the higher the R value, the lower the U value. So you want to have something that has a lower U value to have the best, to be the best at minimizing the heat transfer across the wall. Okay. So this is, again, this particular power kind of gave you just an idea, so to say, or just a quick background. I shouldn't probably say quick because it was quite a while. Quite a few slides that we went through here. but just to kind of give you an overview of civil engineering materials, just to kind of refresh your mind about everything that's should be or will be discussed, or possibly could be discussed, I should say. Not everything will be in an FE exam related to this topic. Again, there's only 4 to 6 questions that are going to be asked in an FE exam related to civil engineering materials, and we covered a lot of stuff here. So some of it won't, obviously a lot of it won't be covered. There will probably only be 1 or 2 things here and there. But it's a good thing just to kind of have in the back of your mind about some of these things as review. All right, if you haven't done so already, make sure you visit the NCEES website. Basically, this is the agency that puts on the FE exam as well as the PE exam. And they do give you a lot of good information in regards to the exam. So if you take a look on the website and you click on the exams, if you look at the civil engineering exam, you click on that PDF, that will actually pop up and tell you what is the different content you can expect in the exam, how many questions from each of the different sections. Now, civil engineering materials obviously is just one section, but you have, of course, mechanics materials, statics, structural analysis, soil mechanics, environmental engineering, hydrology, fluid mechanics, and the list goes on. So you kind of want to know what are the different topics I'm expected to know within each of those particular disciplines so that you could be ready for it on the exam. Some other things that you see over here on the left are things like how does scoring work, some exam prep material. So they do have practice exams that you can take online and pay for to do so. They have practice exam books. They have reference guides. Right here under FE Reference Handbook, this is the actual reference handbook that you will get for the exam. And it's a free download. So I encourage you to actually go to this particular site and download the entire reference manual and kind of have a good idea of where things are and how to use the manual, just to make sure that that's not your hiccup, so to say, on exam day, is not understanding where to find things in the manual that you're ready for that. Okay. Also, where the testing center locations, where they are. Also, what to expect on exam day. That's often a question that people have. What are you going to expect? What can I expect that day? So it goes through and tells you, how much time you have, how many questions you're going to see, when you get a break, things like that. Those are things that you kind of want to take a look at. So when you get a chance, go to the NCES website, take a look at what to expect with the FE exam. And there's also an area over here for registration. And as you can see right here, when it comes to the FE exam, registration is open year-round. So you actually can register for the exam at any time you want for a future exam date. Okay, so you can register, for example, in October for an exam date in January, if you want, or for an exam date in April. Okay, so I mean, it's open year-round, so you can always register at any point in time to take the exam, provided that obviously any future date, I should say, not any current date probably. So anyway, so again, if you get a chance, please take a look at this particular site because it will tell you a lot about the FE exam. Even if you're not taking the FE exam within the next year or so, it's still a good thing to kind of just take a look and see what you can expect to have to take at a later date. Okay. So hopefully this video gave you a little bit of a background, a review, so to say, of civil engineering materials and the different things that possibly could be asked on the exam. But like I said, a lot of this material probably won't be because there's only 4 to 6 questions in total. So good luck on the exam. I hope everybody does well, and have a good day.